Hello, good morning. Welcome to our SAM webinar. We will start in a couple of minutes, exactly at 10 o'clock. So let's wait for some time. Everybody joins. Can you please turn off your cameras and mute your microphones? Okay. See, some people are arriving. Okay, maybe we can start now. It's exactly 10 o'clock. Hi. I would like to welcome everyone to our 15th webinar organized within the scope of SAM project. As you may already know, SAM is an EU-funded project with the target of developing a sector skills strategy in AM. Before starting, I would like to remind that the session will be recorded. The recording and the presentations will be available to those participating after the event. Please stay on mute to avoid any kind of disturbances during the presentations and keep your camera off. My name is Kindermann and I'll be moderating this webinar. And before proceeding further, I would like to express my condolences for all those who lost their lives because of the earthquake in Turkey, and all my best wishes for a rapid recovery for those who suffer from this horrible catastrophe. Unfortunately, one of our speakers, Akin Orhangül from Turkish Aerospace Industries, had to cancel his presentation due to this disaster and is not able to participate today. Let's cross fingers for the success of all rescue teams now in Turkey from Greece, Russia, Germany, USA, China, and many others. Okay. AM, additive manufacturing, or also commonly known as 3D printing, is one of the key enabling industries for sustainable economic growth, being widely used in a wide range of industrial applications. The average annual growth rate of worldwide revenues produced by all products and services over the past 20 years is more than 25%, where the growth within the last 4 years from 2018 to 2022 is about 20%. The world GDP growth average for the same period was only 2.2% at the same time. According to AM Power's report, the total AM industry achieved a size of 8.3 billion euros by the end of 2021, and it's expected to reach a size of 19.2 billion euros by 2026. As a result of such high-speed growth, the demand for qualified labor force in AM has been an urgent necessity, which eventually called on the SAM project to bring in a solution. So, to stay updated on the development of the sector skills strategy and the AM world in general, please follow the SAM project activities through its website, Twitter, Facebook, and LinkedIn accounts, as well as the AM Observatory as the one-stop shop for all the latest news on the AM world that you can also reach from the project website, skillsforam.eu. You can also join SAM project working groups as an associated partner or as an expert. In today's webinar, we will focus on AM in aerospace. We will see some results of the SAM project and at the same time explore the topic from the different perspectives of industry, academia, and research experts. I encourage you to type your questions in the chat. I will collect them and eventually direct them to the speakers during the Q&A session at the end. Okay, now we can start. Our first speaker is Adeline Riou. Adeline is Global Sales Manager in Aubert Duval, and also she's co-chairing Euro AM sectoral group of EPMA. Actually, we prepared a presentation together with her, and we will, let's say, give a short briefing about, Adeline will give a short briefing about EPMA activities. And before that, I will give some information about the SAM project, and then we will finalize his slot by some interesting case studies, especially from AM. So good morning, Adeline. You can hear me, I think.
Good morning, Kenan, and good morning, everybody.
Yeah, thank you for joining. Okay, so this is our short agenda, but as I said, unfortunately, Akin will not be able to join. Now we can continue with our agenda as possible. So let's start firstly by our explanation, let's say, of the activities for the SAM project and what we have been so far in this big project. So maybe you can change the slide, Adeline. Yeah, okay. As you all know, SAM is an Erasmus Plus project with 17 partners all around Europe, with industry representatives, education and training providers, and umbrella organizations like EPMA, Sisimo as well. The coordinator is the European Welding Federation. The project is supposed to be over by the end of 2022, but it is extended to end of June of this year. Next slide, please. Adeline, yeah, okay. So in SAM project, one of the biggest achievements was the development of an international AM qualification system, which is named as IAM-QS, which will ensure the transfer of knowledge process, which is in a harmonized way for every organization internationally. Also, the IAM-QS provides a way to recognize technological knowledge for AM personnel. It supports through innovative training guidelines that cover the front-end emerging technologies AM at an industrial level. It addresses specific industry needs and involves trainings from industry and case studies based on real industrial issues. And also it is recognized as a best practice of international qualification system by European Center for Development of Vocational Training. So next slide, please. So these are the AM qualifications that has been developed up to now, together with the SAM project and as well as previous projects that are the ancestors of SAM. Profiles of AM process engineer, AM supervisor, AM operator, and AM designer has been determined. Their qualifications has been investigated and kind of listed and prepared, and still some work is going on some other profiles for the AM-QS system. Next slide, please. As you may already have followed such activities of EPMA or Euro AM Group, we organized some SAM free courses last year, I think the year before as well, for developing the competence units as a kind of piloting training courses. They all worked quite well. In total, we had 28 hours of lecturing and more than 170 students attended these courses. And these are all now a kind of accredited or certified course programs within the harmonized system of IAM-QS. So you can follow all the recordings of these courses on EPMA website. Can everyone see the slides? I think it's all okay. Bruno, can you see the slides? Okay. Yeah, we see it sometimes, Adeline. Yeah, okay. So as a summary, these are all the activities in the SAM project where we are going to soon make a conclusion. So this is all I can say about the project that is going on. Adelaide, maybe I can give the floor to you now.
Thank you.
Then you continue with our presentation, some words about Euro AM activities, and finally some case studies from AM. And by the way, I see you directly in the screen. Maybe you can turn the camera off. I don't know how to handle it.
Yes. Okay.
Yeah, now it's
no
gone.
problem.
Thank you. Now it's okay. Thank you. Yeah, the floor is yours. Okay.
Thank you, Kenan. So I'm going to speak now in my role of co-chair of the Euro AM group, which was created 10 years ago, in fact, in 2013. And in the absence of my co-chair, Klaus Armondkopf, who finally couldn't join the webinar today. So I'm going to highlight some activities planned by the group this year. So one is organization, of a Euro AM seminar in May, which will be on site again after a few years of online webinars. The webinar will be on from the 9th to the 11th of May in France, in the city of Metz, in the northeast of France. And the key topic will be metal powders in additive manufacturing, and also some highlights of AM processes and advanced materials and emerging technologies. It is organized together with the French Institute IRT M2P. So this is one key event. We'll have then, of course, the European conference in October, which will take place this year in Lisbon, in Portugal. Another key point is the publication of the 4th edition of the Introduction to Additive Manufacturing Technology brochure. It's a document which was first released in October 2015. And we plan to release this year the 4th edition in order to update different chapters, in particular the technology chapter, improving the chapter about metal binder jetting and other sintering processes involving metal powders for additive manufacturing, as it has been a lot of new activities in this field. Also update the EBM chapter, the SLM chapter, and so on. So in this brochure, which we just revamped a little bit for the World PM event in October 2022, we plan also to include new case studies. And as it is today a webinar devoted to aerospace, I just wanted to remind some of the case studies which were included in the previous edition. So one which is quite well known of MTU based on the nickel 718 of a boroscope boss, so which is put on a casing and produced by Additive Manufacturing. It's a series part production. Second one, which is was provided by RSC Engineering on RSC emission rake, also in Inconel 718, where we can see water-cooled channels, complex ones, which can be produced thanks to the additive manufacturing technology, including also thin walls, which is improving the cooling performance and also the cost, providing cost savings. I wanted to highlight some of other case studies. So here, a jet pump made with stainless steel 15.5 pH by Liber Aerospace and Fusia, now Freycinet in France, for airflow inside air conditioning pact of aircraft. So this is aircraft application again. with a part which is providing design freedom to reach optimized airflow. This is one of the key advantage here of the additive technology. Another case studies is a gearbox bracket, here made with titanium TA64 material by Airbus helicopter, Fraunhofer IFAM, and Technical University Dresden. And the benefit is here to provide complex geometry and also integration of function, as it is in one part, two parts made together, and with a weight reduction significant of 40% thanks to the redesign by topology optimization, which is enabled by to produce thanks to the additive manufacturing technology. If we go upper in space, then here we have also two nice case studies, one from Ariane Group and Volumi about casing for Prometheus engine made with 718 material. So this is a quite massive part, as you can see, which was produced on an EOS M400 machine, and showing the design capability offered by additive manufacturing, in particular to minimize the supports for a large component. On the right, you have a thrust chamber designed by Cellcore and produced with SLM 280 machine by SLM Solutions, which is also an impressive part regarding, in particular, eighths of 110 millimeter. And made with Inconel 718, which offer significant advantages versus conventional part manufacturing, and in particular the integrated design, the mass reduction, and the time saving. And if we go even higher in space, in satellite application, I wanted just to show again some of the satellite-related case studies we have in this third edition. One is a satellite bracket made with aluminium material by Riou and EOS. Here, again, using optimization of the design to provide lighter and stiffer components, and produced on a large EOS M400 machine. Also with integration of function, as we have here two parts in one, and so the weight reduction of 40% compared with traditionally manufactured bracket. And on the right is another bracket here made by Thales Alenia and 3D System with titanium material, which is also redesigned to achieve a better weight saving in particular, and faster production. So these were some of the case studies highlighted and relate in the current edition of the Introduction to Additive Manufacturing Technology brochure. And we are in the process of collecting new case studies. Here I wanted to show a few of the new ones we will publish in the next edition, and call for a contribution if you have more case studies to provide for aerospace, but also for additive, for other segments. So here is one original case study of a magnesium part with a very light weight of 520 grams. Produced, which is a vertical lift part, which is developed together with the Boeing company by the NLR laboratory in the Netherlands. And the benefit is here, of course, mass reduction, thanks to the combination of design by additive and the use of this magnesium material. Another case study is here supplied by University of Paderborn with airplane gimbal made with TEI-64 material. And the concept of this work has been to increase the speed of manufacturing, in particular, with by the additive reduced exposure time, and also implement a heat treatment to reduce the pores. And this component, thanks to the high-speed manufacturing approach, has been produced in 38 hours instead of 49 hours. Which is beneficial for the cost, for the time as well, and providing increased component complexity, and it has also a positive impact for sustainability. Another case study which will be included in the brochure is a combustion chamber for a rocket engine, liquid-fueled rocket engine. This is made with nickel-based ABD 900 AM material. It's a part with eighths of 291 millimeter. And it was successfully fired by Airborne in March 2021. The benefit of additive manufacturing in this application is integrated design, the ability to provide the thin walls and complex cooling holes, and the high temperature strength provided by the ABD 900 material. And this was done in collaboration with Riou and Lloyd in UK. And last, a new case studies, again with ABD 900 material, of an injector for rocket engine produced by laser beam melting for a LOX methane engine. And this is for original application by a company Dark of a new launcher concept, as you can see, of a reusable rocket, which is flying or taking off from a plane in altitude. So saving on the engine and launcher weight, thanks to the initial flight with an aircraft. So this is a new concept, and the injector, thanks to the use of high temperature material ABD, can have a better performance, in particular in view of the reusability of the engine, which is a key point in additive manufacturing. This was done in collaboration with Volume in France. So these are some highlights of aerospace case studies. We plan to release a new edition of the additive brochure in October at European in Portugal, and we will be glad if in the audience you want to contribute, or if you know people who could contribute with more case studies. The end of submission is in March, and we will welcome case studies for not only aerospace, but also energy, medical, industry and tooling, automotive and car racing, or consumer goods, any original application, to demonstrate the interest of additive manufacturing with metal powders is useful, as it has been a lot of progress in applications of the technology since the last edition of 2019. And the contacts to contribute, as repeated here, so Kenan from EPMA, myself, and Klaus Aumond-Kopp, my co-chair for the EuroAM group. Thank you.
Thank you, Adeline. So as you can see, please either contact me, Adeline, or Klaus. The mails are here, email addresses are here. If you want to submit and present a nice AM part as a case study to be taking place in the publishment of the 4th edition of our famous Introduction to AM brochure. Okay, so
Thank
if
you.
you have any questions to Adeline, thank you, Adeline, once again. If you have any questions to Adeline, please do not hesitate to put them in the chat. I will later on collect these and direct to our speakers. Thank you. Now I would like to pass on to our second speaker. This is Paul Davies from Sandvik Additive. Paul is the technical solutions manager, and now he will speak about metal powders for AM aerospace applications. So hello, Paul. I think you can hear me.
Good day. Yes. Good day, everybody.
Yeah. Good morning. Good day. So, okay, you can share your screen and the floor is yours.
Thank you. Is the slides coming through to you okay?
Just wait.
As I said, the title of the
Yes,
presentation is Gas Atomized Powders for Additive Manufacturing with a focus on aerospace applications. So I'll proceed to the contents of the presentation. If my view is blocking the slides, I'll cut the camera shortly. But first of all, we'll talk about powder production processes, then alloy powders for aerospace applications, optimized for additive manufacturing, and then a few examples of some aerospace applications with a focus on space this time as well, and then finish off with summary and conclusions. So now I'll kill the camera so you can see the full slides. And there we go. Okay, so first of all, I'll start with Sandvik's materials evolution over time. So Sandvik's been involved in the metals industry for more than 160 years, actually, evolving from steels and carbon steels for the rail industry originally to stainless steels, then advanced stainless steels such as super duplex, which is heavily used in the oil and gas industry. Powder metallurgy then started to make an impact on the kind of the volumes of materials that we started to produce, and the interest in nickel-based superalloys for aerospace, and then super alloys, which are of course melted under vacuum, mainly nickel-based alloys, and more recently titanium alloys. So now looking at powder production processes. Plasma atomized powders is a well-established production process for manufacturing of gas atomized powders, typically using argon gas. And the raw materials for this process typically include wire-based feedstock, imported into the plasma atomized facility from a spool. So therefore, there's a wide range of different materials available, but of course it does rely on a wire-based feedstock. And here you can see an arrangement of plasma torches, which provide both the heat to melt the feedstock and the gas supply to atomize the powder. And plasma, at the end of the day, is basically very hot gas. And a very well-established process for additive manufacturing as well, providing a range of different sizes, typically a coarser to mid-size fractions. Then we have a very well-known process called plasma rotating electrode production process. So this, again, a very long-established process where, in this case, the raw material is an electrode, a rotating electrode, and again, using a plasma arc to both melt the raw material and also then to provide gas to create the particle surfaces. And of course, because it's rotating, then of course the forces involve spin off the powder particles, and then they're captured in a kind of cylindrical construction. This process typically produces very spherical powder and generally of a coarse fraction. Typically used in the medical as well as the aerospace industry. Now I'll move on to inert gas atomization, which from a volume production process, inert gas atomizing produces the highest volumes of powders for many different applications in aerospace, including hard surfacing and thermal spray materials. Originally, back more than 30 to 40 years ago, actually producing these types of powders for coating turbine blades, for instance. And many other applications, and has diversified into, for instance, powders for metal injection molding, and more recently to additive manufacturing. So here you can see the construction of a typical inert gas atomizing facility. The raw materials are typically alloyed in a coilless induction furnace. This is often prepared in a melting closure of inert gas in many cases. So that provides often a partial pressure to protect the molten material from oxidation, for instance, and reduce the levels of slag generation and oxides. Often using nitrogen gas, which is, of course, the lower cost gas compared to argon atomization, but both are typically available on these types of facilities. So the molten material is sourced from scrap materials or alloyed in situ to create a diverse range of different materials, typically top poured, sometimes bottom poured, into a tun dish of usually a conical shaped tun dish, and the molten material then is drawn into the atomizer and impacted by high pressure gas, which can be in various different arrangements, from close coupled atomization of fine powder to two-stage atomizers for mid and core size fractions. So you can atomize different size distributions based on the configuration of the atomizer. So the atomization occurs in this enclosed vertical chamber, and is often water cooled, and the gas to metal flow rates are balanced to optimize the performance and efficiency of the equipment. By the time the powder particles, which break up under the pressure of the gas, reach the bottom of the chamber, they've typically solidified with relatively fast cooling, but still slow enough to form a spherical shape. And then the gases and the particles are separated in a cyclone, where the gases are exhausted and the powder particles are collected in a collection. This does allow the configuration to have recycling of the gases, and for argon that sometimes is justified in terms of the capital equipment investment. So as I mentioned, it has the gas atomized powders have a spherical shape which impart good flow characteristics. Because of the melting closure and the relatively clean process, metallurgically clean, provides a good performance when it comes to mechanical properties. The powder has a broad normal size distribution, as you can see from the diagram here, and a very spherical shape, a range of different sizes of particles, and that provides a good tap density or packing density. And that can be very advantageous when it comes to additive manufacturing to provide uniform layers with a good flow characteristics. So moving on from inert gas atomization, the premium process is the vacuum inert gas atomizing facility. So a similar configuration, but in this case, the atomizing, the melting process is completed, often top pouring again into a tun dish using a hermetically sealed chamber, where the various alloys can be trimmed and samples taken, but certainly is a very efficient and clean process metallurgically when it comes to the melting process. Because it's done under vacuum, that does produce much less oxidation of the melt, and that in part produces improves performance. Of course, you can't atomize under vacuum, so you have to typically backfill with argon gas. And most of the vacuum inert gas atomizing facilities run with argon atomization, but sometimes nitrogen is also available. And here you can see an example of a superalloy Inconel 718 powder with a size distribution of 15 to 53 microns, and a median size, a D50, around about 32.7 microns. So next I'll provide a little animation of a process called electrode inert gas atomization. So you can see the electrode at the top. Again, in this case, it's a bar stock material. It's inserted into a electrode. It's a copper electrode. It's actually hollow. And that induces an electrical current or eddy currents in the electrode to melt the molten material. That electrode actually is produced by additive manufacturing. See its complex shape. And then the molten material free falls into the atomizer. In this case, it's titanium, so it has to be a refractory-free process. The atomization gas then impact on that flow of molten metal material. As it falls through the cooling tower, it solidifies, and again, the powder is separated from the gas, and the powder is collected. And in this case, often the titanium powders produced by electrode inert gas atomization are handled under complete inert conditions. So the blending and sizing and packing are all done under argon atomization, argon gas. Just to highlight Sandvik's facilities in this area, so we have inert gas atomization in the UK, 10 inert atomizers actually, and have been producing powders at this location in South Wales, the Osprey facility, for more than 40 years, employing both argon and nitrogen atomizing. And we have a range of different size distributions, from average size of 5 microns up to 80 microns. So therefore providing powders for different applications, aerospace approved, and have various ISO standards associated with health, safety, environment, and the energy, and ultimately providing credibility when it comes to sustainability. In Sweden, there is a vacuum inert gas atomizing facility, mainly producing nickel-based superalloys, although has the capability to produce various different materials from copper alloys also, and the electrode inert gas atomizing facility, which is dedicated to titanium alloys typically. Nitrogen argon atomization. The plants typically are slightly coarser in terms of the average size distribution, from 20, and then coarser powders for applications like hot isostatic pressing. And this facility is AS 9100D Aerospace approved, and also has some medical certification for the titanium powders. And when you produce powders, of course, you want to evaluate their performance. Sandvik has an additive manufacturing center of excellence in Sweden. This has capabilities in laser powder bed fusion and binder jet printing. And then Sandvik also has links with some of the largest European additive manufacturing service centers based in Italy, from the BMIT facilities and 3T in the UK. Okay, now moving on to the range of alloy powders for aerospace. They certainly are comprehensive. Inert gas atomized powders are typically producing stainless steels, and 316L and 174pH account for the vast majority of the stainless steels produced. Super duplex and duplex stainless steels, Mar aging steels, which were invented in the 60s and have found applications back then for landing gear in aerospace applications because of their high strength and high toughness, and have had a renaissance in additive manufacturing, typically because these materials have high strength but don't rely on carbon to impart that strength and hardness in particular. They are Mar aging using intermetallics of nickel and cobalt and molybdenum. So they found a renaissance because they can be processed very well by laser powder bed fusion. Low alloy steels, of course, there's many different specifications, and a few are now finding their way into additive manufacturing, especially case hardening steels. Tool steels, hot work tool steels in particular, are popular in additive. Cobalt alloys, of course, medical applications for aerospace. Copper alloys, controlled expansion alloys, high temperature materials like Vicralis, soft magnetic alloys, aluminium alloys, and many more. And then we compare with vacuum inert gas atomizing, employing the process to manufacture nickel-based superalloys, so Inconels, as well as many more. And there is work going on to expand the range of nickel-based alloys. Copper alloys have also been applied, including copper chrome zirconia and alloys developed by NASA called GR-COP42. So these are copper chrome niobium alloys. So they're stable at high temperature, but still impart good thermal conductivity. Electrode inert gas atomizing, typically producing titanium alloys. Of course, the workhorse of this aerospace industry is titanium 6 aluminium 4 vanadium, as well as commercially pure titanium and alloys related to the aerospace industry like titanium 6242, which have a slightly higher strength than titanium 64 and operate at a higher temperature also. Zirconium alloys as well are also possible and used in the nuclear industry. And then plasma atomizing, titanium powders, titanium aluminides, titanium nickel, like shape memory alloys, and titanium niobium. Cobalt alloys, copper alloys, nickel alloys, and as well as refractory metals, tungsten, niobium, and tantalum. And there are many others. And one final process to mention is the hydride-dehydride process for manufacturing titanium alloys. And now I just thought I'd highlight the alloys that are relevant for the aerospace industry. Of course, you have stainless steels, which can provide general purpose materials, having a combination of strength and corrosion resistance and relatively low cost. For ultra high levels of hardness and strength, Mar aging steels can find applications. Cobalt, nickel alloys and nickel alloys are both super alloys. Copper alloys for, as we'll hear later, about rocket applications. Controlled expansion alloys like Invar 36, particularly useful in low temperature environments like in space. Of course, high temperature materials used in aero engines and aluminium alloys for light weighting. And then, of course, we have the nickel-based superalloys and for aero engine applications, and copper for rocket nozzle applications. Titanium for its combination of strength, weight, and corrosion resistance. And yes, likewise, titanium, cobalt, copper, and nickel-based alloys are available in plasma atomized powders also. So now comparing the different types of powders in terms of gas atomized, vacuum gas atomized, even water atomized, are popular in metal injection molding, and plasma atomized. So you can see there's various morphologies of the powder and that impart different properties. So of course we have to consider cost of the process. Inert gas atomizing is generally the lower cost, higher throughput in terms of volume and flexibility. Powder flow is an important characteristic, especially for layer-based systems like powder bed fusion and electron beam. Entrapped gas porosity, especially for coarser powders, the oxygen level, and no doubt there is an advantage for vacuum melting as well as plasma atomizing. The wide range of different materials available, certainly dominated by inert gas atomizing with its flexibility in terms of alloying. And then the size range available, inert gas atomizing has been optimized for producing various different size ranges. And there's some advantage there, especially when it comes to fine powder production, typically in binder jet printing. And then packing densities and of course compatibility with different additive manufacturing processes. So the powder attributes Key factors when purchasing powder, so the shape and morphology have to be taken into account, the degree of satelliting, which can impart issues related to flow characteristics, and often the atomizer's process has been optimized for the specific applications. So anti-satelliting technology has been employed in inert gas atomizing now for many years. The particle size distribution and its flow characteristics are important. Issues such as humidity, and the Euro AM has a project which is starting to investigate the effect of humidity and flow characteristics. Humidity here, we can see the different size distributions and the effect of Hall flow rate. As the average size drops, typically the flow of the powder becomes poor until effectively, if you try to measure it by a Hall flow meter, it becomes very difficult, if not impossible. And then batch-to-batch consistency. This can be for both size distribution and also the chemistry, and I've highlighted here oxygen content, for instance. And the starting oxygen content can have an influence on the use of the powder in service during laser powder bed fusion. After a time, of course, it will pick up more oxygen. So having low levels of oxygen in the initial powder sometimes is an advantage. And that's where vacuum melting in particular can be very attractive. Once you understand powder attributes, then of course you have to develop test methods for establishing chemical composition, and analyzing the composition of powder is sometimes challenging. You have to develop standards and processes specifically for metal powders. Size distribution, laser diffraction, and sieve analysis are very well established, and flow meters. Hall flow meters, Kearney flow meters, and even more recently, rotating drum methods of understanding the flow of powders is becoming very important. Especially as the technology related to powder bed fusion is very much reliant on flow characteristics. And then we have other test methods for density of the powder, tap, apparent density, morphology, microstructure, and thermal conductivity. And when you have done some testing, of course, you need standards to measure these tests, of course, and there are a growing number of test standards. Here's a few examples from the ASTM for sieve analysis and sampling, oxygen and nitrogen content in titanium alloys, for instance. And there's a growing body of standards where the aerospace industry can ensure that reproducibility and conformance is important. And yeah, ISO standards who are now linked directly when it comes to additive manufacturing to the ASTM committees as well. And I myself represent the British Standards Institute as a representative on many different standards committees. And currently we're working on standards for Inconel 625, for instance, as well as stainless steels. So now talking about one particular aspect, powder size distributions, of course, atomizing fine powders as well as mid-size fractions and coarse powders. And these can be atomized, targeting the different distributions for the different additive manufacturing processes. Fine powder typically used in metal injection molding, but also now finding interest in binder jet printing. Of course, the laser powder bed fusion, electron beam, and direct energy deposition processes, and even courses or full fractions used in hot isostatic pressing of net shaped components, but also a very useful technique for, of course, consolidating the microstructure and eradicating pores. So optimized for additive manufacturing. So here you see the setup for a vacuum inert gas atomizing facility, producing powders for additive manufacturing and hot isostatic pressing. It is, compared to an open furnace situation, a much cleaner and safer approach, and I'm sure over time more and more facilities will be adopting the vacuum inert gas atomizing process. It is currently producing a very wide ranges of different atomized powders in Inconels, nickel-based alloys, as well as more advanced grades like Hastelloys and Rene alloys and MARM grades as well. And these are currently being optimized for the laser powder bed fusion process. Some of them are not weldable and therefore present challenges when it comes to producing the appropriate microstructures free from cracks. And custom alloys are being developed. Other alloys include specialist clean materials like INVAR 36. And the advantage of melting and vacuum, of course, is low oxygen and low nitrogen levels. So taking one example of this 718 powder, here you can see a typical morphology of vacuum inert gas atomized. It is a precipitation hardened superalloy. Melted under vacuum, then inert gas atomized. It has a combination of high strength and good corrosion resistance and can operate up to 650 degrees C. Here presenting some properties comparing inert gas atomized Inconel 718, which is a slightly lower cost process compared to vacuum inert gas atomizing, especially from a capital equipment point of view. And here you can see the properties of mechanical strength in the vertical direction for yield strength, tensile strength, both at ambient 20 degrees and 650 degrees C. Mechanical properties, elongation, and ultimately the vacuum inert gas atomized powders is found to be slightly superior in terms of elongation and in toughness, and no doubt when it comes to fatigue and creep performance, the lower levels of non-metallic inclusions in the vacuum inert gas atomized will be highlighted in these types of dynamic test criterion and will show superior properties compared to inert gas atomized powders alone. However, it does depend on the application. For oil and gas applications, inert gas atomized is a cost-effective process, whereas for aerospace qualities, often vacuum is a pre-requirement. So, and that means there's a full material set of information in terms of the yield strength, tensile strength, elongation, and impact toughness. And these are available in different size distributions for all of the additive manufacturing processes. And of course, aerospace, gas turbines, and oil and gas applications. So now moving to Hastelloy X, another popular product, but does suffer from cold cracking during the laser powder bed fusion process. And here we can see some evidence of cracks in the microstructure. So some work was done and some research was done to establish an optimized composition for inert gas atomized, where no cracks are evident in the microstructure. Then in particular, manganese and silicon were found to influence the crack formation as well as corrosion resistance. And also a vacuum inert gas atomized powder was developed where there are no cracks in the microstructure, which of course is very important. Comparing the properties, here we see a comparison of inert gas atomized and vacuum inert gas atomized powders at 20 degrees, as well as operating at high temperature at 850 degrees C. And you can see yield strength and tensile strengths provide very good performance. And yes, there's definitely advantage when it comes to vacuum inert gas atomizing at high temperatures. However, at ambient temperatures, there's not much difference between them actually. Yes, so optimized composition reduces the presence of cracks. The elongation is comparable. Elongation and modulus was enhanced by heat treatment. Both inert and vacuum produced powders had good impact toughnesses. But really, when it comes to aerospace, having lower levels of non-metallic inclusions, there's definitely advantage for vacuum melting. Again, producing a range of certified material properties operating at up to 850 degrees C. So yields and tensile strengths and high elongation, in this case, up to 40%. And again, available for all the different additive manufacturing processes and relevant to aerospace applications. Now moving on very quickly to another example, Inconel 625 has very high corrosion resistance and can operate at high temperatures. And yes, good when it comes to critical corrosion as well. And electrode inert gas atomizing. So here we can see, as I said, dedicated processing of the material under inert conditions, producing wide range of different sizes, from hot isostatic powders to powders suitable for the direct energy deposition or electron beam melting and laser powder bed fusion, and a growing interest in fine applications for metal injection molding. And there are now some initial machines in binder jet printing that are producing titanium components as well. And what does the titanium powder look like? A very spherical powder, actually, and has a range in this case of 63 to 20 microns, and good flow characteristics. Of course, titanium has a relatively low density, so flow is impacted by its kind of density as well as its morphology. In this case, it has recorded a whole flow result at 38 seconds for the 50 grams, but this was with the aid of a flow aid. Typically added as a nanoparticle, less than 100 ppm, with a compatible composition in many cases. So it's very hard to detect, but that guarantees good flow characteristics, and so far has no impact on final mechanical properties, although there's still more work to do in that area. Available with and without flow aids, I would say. Comparing plasma atomized and electrode inert gas atomized, very little difference in terms of morphology and flow characteristics, and the size distributions are very similar, as well as the oxygen and nitrogen contents, which are crucial in terms of mechanical performance. Titanium alloys. Here we see different layer thicknesses from 60 microns and 30 microns, optimized for the electron beam process. And moving from 30 microns to 60 microns effectively doubles the speed of the processing. Titanium powders have then been optimized in terms of the surface contours, the bulk density, and surface roughness. Microstructures before and after hipping are available, and here's a comparison between electrode inert gas atomized and plasma. Very little difference in terms of the microstructure, where you see the alpha beta microstructure in the typical Widmanstatten basket weave type structures. And then comparing the yield strength for the two different processes, plasma and electrode inert gas atomized. Very little difference in yield strength. Toughness may be a slight advantage when it comes to the electrode powders. And then when we have powders then produce at different layer thicknesses, 30 microns and 60 microns, little difference between the mechanical performance, slightly better perhaps when it's at 30 microns, and the elongation actually slightly better when it's a 60 micron layer thickness. And then comparing the properties, here we have the tensile test for titanium 6-4, and there's definitely advantage for hot isostatically pressing. Not so much in increasing performance, but in fact in improving the reliability of the statistics. So it reduces the variability of the titanium. And this is all available from various different sources, documenting the heat-treated and hot isostatic press material performance in terms of tensile strength, elongation, elasticity, toughness, hardness, as well as surface roughness. So there's a growing body of materials available for laser powder bed fusion, and this is an example from the EPMA. So we have the aluminium alloys, stainless steels, nickel-based alloys, cobalt, titanium, and then we have the ultra-high hard and strong Mar-aging steels. One example comparing different materials. Here we have an aluminium alloy, a relatively new alloy, scam alloy, and comparing to titanium 6-4. So specific strength, titanium has the advantage. And likewise, when it comes to specific strength, titanium has the advantage here also. And then if we compare density, however, aluminiums, of course, have a lower density compared to titanium. So that has you have to take all these factors into account when you're designing components. And here's an example of a brake caliper, optimized design for both the material performance and capabilities in terms for aluminium alloys and titanium and scalmalloy. So you can see complex structures there and generating a final component with optimized weights and performance in terms of its safety performance, in terms of approximately 60% of its maximum tensile strength. And then balancing the material properties, the density, and the cost of the materials, you can select the appropriate material for the application. Moving on to some aerospace applications, so I'll finish up very quickly. Here you can see various applications for additive. We saw a few examples of the fuel nozzle, the borescope, many door locking applications, CE alloys, controlled expansion alloys, direct energy deposition for vane repair is becoming popular, and Inconel blisks laser powder bed fusion printed, and of course have to be machined to produce that surface quality and resolution and tolerances. So there are emerging applications for lightweight near-net shape. Here we see a blisk designed by Sequel Tools in titanium 6, aluminium 4, vanadium by laser powder bed fusion. And yes, very good surface quality, and printed in one part as well. So that's definitely an efficient process. Some other aerospace applications, Pratt & Whitney have been involved in powder metallurgy and metal injection molding for many years, and some of their new pure power engines for the Bombardier aircraft are incorporating metal injection molding. And now they've stated that they have more than 100,000 prototype parts in additive manufacturing, many no doubt in polymers, but certainly more and more in metals, where they were employing both electron powder bed fusion and laser powder bed fusion processes. And in production tests, Pratt & Whitney stated that they've realized time savings of over 15 months and up to 50% weight reductions in a single part. So that's the typical aerospace and aero engine applications. Now we'll move on to the space technologies, or the space part of aerospace. And of course, we're all familiar with the European Space Agency, doing basic research, looking at discovery and applications, and employing technologies from different TRL levels, technology readiness levels, for their applications. Here we see Themis, Prometheus, and other rocket nozzle applications, and in development are the launchers themselves. So just some recent news derived from Metal AM. Here we see a Vulcan extension hardware nozzle. This was produced by GKN in a program funded by the Ariane group. And Ariane is, of course, a major European rocket launched from Central America, but it's a wholly developed European program for both heavy and light payloads into space for applications such as Earth observation, becoming ever more important with global warming applications, telecommunications, meteorology rather, and navigation. And GKN in their Swedish facility have been working with Ariane for many years, for decades, almost 50 years. And now they're involved heavily in additive manufacturing for the rocket nozzles, which incorporate different cooling channels. And I'll show some examples. So here's that was the Vulcan. Here's another engine, the Prometheus. Again, the GKN are working on this, and there are 14 Ariane launchers will be manufactured from now in the next couple of years. So it's a very important application, and there are over 1,000 combustion chambers and nozzles required. And as well as that, there's the turbo components to the pumping the fuel, of course, operating under extreme conditions of high speeds and low temperatures. And I'll finish off with just one more application. Here we see a a rocket nozzle called an Aerospace. And Boeing have also highlighted that they have more than 1,000 parts in their satellites. But I'll focus on the Aerospace engine. So it's a development from the 1950s, has found renewed interest because of its at the time in the 50s, they couldn't really produce it economically enough. But with the advent of additive manufacturing and printing processes, with being able to incorporate the cooling channels and the complex internal structures, this type of rocket nozzle has found a new lease of life. And also the materials applied. You see, it's a copper color, typically a copper chrome zirconium or a copper chrome niobium. And here you see a couple of examples of the different materials. And GR-COP42 is the copper chrome niobium alloy developed by NASA, the Marshall Space Center. And the advantage of this materials is it maintains its performance and strength, even though it's not that strong, at higher temperatures, while having a good thermal conductivity, again, operating up to high temperatures, up to its melting point. Melting point, of course, is about 1080 or 1082 to be precise. So therefore, it has to have internal cooling structures to maintain its material integrity. And the advantage of the Aerospace nozzle compared to the classic bell shape is it performs better at lower altitudes, where actually the rocket has most of its fuel and is heavier. So therefore, that provides some performance capabilities compared to classic bell shape rocket nozzles in terms of the expansion of the gases from the rocket. And here we can see the application. Of course, it operates at very low temperature, but when you turn it on, it gets very hot, as you could imagine. So in summary, gas atomized processes were introduced. Materials are manufactured using clean induction melting technology, incorporating a wide range of different materials, from stainless steels themselves incorporating a lot of recycled material, copper alloys, cobalt alloys, as well as classic nickel-based superalloys, copper and copper alloys, including the GR-COP42, and titanium alloys, including new alloys like titanium 6242, which are now available in powder form. These have all been optimized for additive manufacturing in terms of powder size range, modified compositions for the process, like the example of Hastelloy X. Process parameters have been developed to increase efficiency, moving from 30 micron layer thicknesses up to 60 micron layer thicknesses, for instance. And all powders generally and alloys generally benefit from heat treatment to make sure that the differences and anisotropy between vertical and horizontal directions is reduced by heat treatment. And the microstructure and material properties achieve high performance requirements for the very demanding service conditions for aerospace applications. So in conclusion, there's a wide range of alloys available for additive manufacturing. Thank you very much, and I'll take questions at the end.
Thank you, Paul. You already received some questions in the chat, so we will take care of that in the Q&A. Also, I placed in a feedback survey that we need to improve the project performance. It's just a 2-minute survey. You can directly go online from the link and link in the chat, and you can take the survey. That would help us to improve the project. As I said, thank you very much in advance for joining that. Okay, our third and last speaker is Philipp Kindermann. Philipp is working as a scientific researcher at Fraunhofer IGCV, and now he will make a presentation on multi-material AM for space applications for cold spray and powder bed fusion. So, hello, Philipp.
Hello, thank you very much, Kenan, for the introduction. And yeah, today I will talk about multi-material for space applications. And yeah, I work at the Fraunhofer IGCV, as Kenan already said. I hope you can see my my presentation. And yeah, we are located in the south of Germany, in Bavaria. And we got three departments, one focusing on composite technology, one focusing on processing technology, and a department for casting. In total, we are around 160 employees. And with a focus on AM, we got around 30 researchers, and we got a focus on AM in all of our three departments. So we got in our AM at casting department, we focus on multi-step additive manufacturing, so binder jetting for producing sand molds and stuff. We got our AM at composite department. There we are focusing on extrusion processes for carbon enforced, fiber enforced polymers. And then last but not least, we got the AM at the processing technology, which is led by Dr. Schlick. Some of you may know him in the EPMI world. And yeah, here we are focusing on the laser powder bed fusion and on DED processes for the fabrication of metal, multi-material metal, and metal ceramic parts. Here we have a short overview of our laboratory. It's a joint laboratory between the Fraunhofer IGCV and the TUM IWB. And here you can see our we got several voxel jet sand binder jetting machines. We got our DED material and material jetting machines. Here you can see the Plasma Geeken cold spray system. I will talk about that later. Here, very interesting, it's a very new process. It's called liquid metal printing. For some of you who are may interested in that, just feel free to ask me later about that. Here we got powder bed fusion processes. It's a we divide between our multi-material capable machines and our standard machines. So on the one hand, we got the machines which are capable of multi-material. This is an Aconity 1, an SLM Solutions 280, and the SLM Solutions 250. And then we got several other, let's say, standard machines. And furthermore, we got our polymer machines, but in the department where I am, we are more focusing, or we actually solely focusing on the metal machines. So let's dive right into the multi-material processing. So what is multi-material processing? Here, we need to distinguish three different multi-material aspects. So first we got the discrete material transition. Some of you may know that it's kind of an industry standard. So also as hybrid manufacturing, some of you may know that. So placing a conventional machine part, for example, into a build plate at the PBF LBM and then build up an AM part onto it. So you got a discrete material transition. And it's kind of it's not low tech, but it's a kind of a simple multi-material application. Then we got the continuous material transition. This works very good with cold spray, as I will show you later. So you got material A and make a continuous transition to material B. This is still in the state of research. And then we got the what we call actually really a real multi-material application. It's you got your material B located anywhere within your material A. So your machine is capable to place your second material anyway within your, let's say, main material. And that's also state of the research. And that's where we are focusing mostly with our PBF LBM machines. Speaking of PBF LBM, so let's dive into the laser-based powder bed fusion. Here we can see the four known till now possibilities for the multi-material powder spreading. So we got on the one hand the holohedral system. So this is operating on, was developed at the Fraunhofer IGCV. Some of you may know it. We got a recoater which is divided into two chambers. So you got one material and another material in the second chamber. You are just recoating or spreading the powder onto your whole build plate. Then the laser is solidifying the first material along the contour. And then the recoater is driving back, and by driving back, the suction unit removes the powder which was not solidified by the laser. Afterwards, it drives once again over it and spreads the material B. and then the laser solidifies material B, and then the building platform is moved down. Then we got the nozzle-based applications. Here you can see you got a fine nozzle which spreads the powder, usually guided by a robot, onto your build plate after it was recoated by a conventional recoater. Then we got our masked applications. Masked means in this case that the recoaters or the application systems are able to spread or to place powder onto the build plate already with the contour or with two materials at once. So not a two-step process, so all in one step. So here we can, for example, got the pressure-based mask systems as it was developed by Aerospace. Here you got two drums which are which got a lower pressure on the inside, so powder is sticking onto the drums, and then a nozzle selectively removes the powder along the contour. And this is done with two drums, so one for material A, one for material B. And then you got the system with the photoconductor. Photoconductor sounds very fancy, but actually it's what you find in all of your printers, all of your laser printers. You got a photoconductor which is charged, then exposed to light, then the charging is removed at the places where you want it removed, and then you can attract your powder to the contour and place it onto the build plate. So here we got some data. This was based on a review paper from my fellow colleagues, which was published in the PM in 2021. If some of you may interested in that, here's the source. So you must distinguish this, especially within the coating, regarding with the coating rate. So here, this system has actually a rather high coating rate, but it's limited due to the fact that it must run over the build plate twice per layer. Of course, the nozzle-based, as it's a fine nozzle, as you want to achieve fine contours, it's a little bit, it's very low. And here with the pressure, with the mask systems, as you can place your powder all at once per layer, it has the highest coating rates. The resolution, how the powder is placed onto the build plate, is very good for the nozzle, but it's still very good for the masked applications. And the part resolution, I will show you later with our holohedral system, is at the moment very, very good. Mr. Davies already talked about manufacturing readiness levels. Here we see the holohedral and the nozzle-based systems in the state of 4 to 5. So it's a working technology, but still in a laboratory environment. The photoconductor system still is on a very, very basic level. This need to be enabled for a real machine use. So let's head on to a bit of our parts over the last years. So this was one of our first multi-material parts. It's called the triplet. It's a very small part, as you can see. It's just 30 to 30 millimeters in the base. And it's made out of a tool steel and copper chrome silicone. This was made on our SLM250, which only had a building or a build plate diameter, or not diameter, sorry, it's a square with a 50 to 50 length on each side. Then in 2021, we managed to build an even larger part. This is the section of a combustion chamber. This was done in cooperation with the Rocket Factory Augsburg. It's a rocket startup here in the area. It's still not that big, and it's still made out of tool steel and copper chrome silicone. I will tell you later why. Then we managed to get even bigger as we achieved our SLM280. So now we are able to build very large parts with, as you can see here, the side length of 280 millimeters to 280 millimeters. And you can also see that the yeah, that this is very very clear, very sharp. So the resolution of the process is very high at the moment. And last but not least, you may know this this part. This was our one of our biggest demonstrator parts at the moment. This is the combustion chamber my colleague designed. It's 120 millimeters in height and still made out of tool steel and copper chrome zircon. That's why, as you can see it here, the powder is getting mixed within the process. So afterwards you got a mixed powder and you need to separate it. So tool steel and copper chrome zircon is very very suitable for that, as the tool steel is ferromagnetic and the copper chrome zircon isn't. So you can we have invented a mechanism which can separate the powders for us. Then let's move on to the progress in microstructure and the material transition. Here we made huge progresses over the last years. You can see when we were building copper chrome zircon onto the tool steel, we got an heat accumulation because the tool steel has a poorer thermal conductivity. So here the molten phases are mixing within the process. Vice versa, it's not that bad, as copper chrome zircon is quite a good heat sink. That's why it's used. And by now, with adapted strategies and path planning strategies for the laser, we managed it to get a rather discrete material transition, as you can see it here, and now in both ways. So it doesn't matter if the copper chrome zircon is on top or the tool steel is on top. So that's a huge progress for getting a fine resolution within the multi-material parts. Yeah, what are the next steps and the parallel initiatives? So yeah, as you may think about it, it's of course that we want to use not a tool steel, we want to use alloy 718 and copper chrome zircon for space launcher applications. My colleague already made some progresses here with this multi-material combination. The problem, as I mentioned, is the separating of the powders, but we are working on solutions here, so we don't have to throw away all the mixed powders. This can go anywhere between mixing, sieving the powders and different grain sizes and stuff, till other more fancy separation technologies. And then we are planning going to the development of our hot firing tests, and we want to identify future use cases and material combinations. And yeah, as it's shown here, the combination of 3 and more materials. So therefore, we can integrate one structural material, so for the structural strength, one insulating material such as a ceramic or stuff, and then a conducting material to enable the direct manufacturing of circuits or the direct manufacturing of sensors. Yeah, that's where we are at the powder bed fusion at the moment, at the multi-material powder bed fusion. So let's head on to the cold spray additive manufacturing. I don't know if all of you are familiar with the process of cold spray manufacturing. So here's a short overview. And yeah, we got a cold spray gun. Within that, there is a heat chamber here. The process gas, which is highly compressed, is guided into here. There it is heated to achieve a higher gas velocity and to warm the particles so they have to thermal soften the particles actually. The powder is then fed into the nozzle here, and then afterwards the powder and the gas stream is guided through the nozzle to the Laval nozzle, and the powder is thereby accelerated to supersonic speeds, and then impacts a substrate, and by impacting the substrate, the particles deform plastically, and afterwards, with the subsequently impinging particles, all the particles form a dense layer, and the bonding mechanisms behind that are a combination of a mechanical interlock and a metallic bonding. And yeah, aside from a reduction of the plastic deformability of the part, you actually all of the properties of your powder actually remain in your parts. So because there is no melting of the parts at any point. So this is actually one of the biggest advantages of this process. It is not cold, as the name may suggest, but it's still not a melting process. Thereby, I think the term cold spray still is sufficient here. Yeah, what do you need for a cold spray system? This is our cold spray lab at the Fraunhofer IGCV. Yeah, let's start on the left. We got 2 powder feeders, 2 because multi-material. So they can be simultaneously supply powder to the gun. Here they are just connected by a Y ventile, and then the material is placed right into the gun here. And the gun itself is guided by a 6-axis robot, and the substrate can be placed onto a workpiece positioner. As the gun gets very hot due to the heating, it's supplied by, it's got a cooling water supply, and the power cables are also water cooled, as they are taking a lot of energy. Let's have a short view on the progress we made over the last years. So here we got our first demonstrator part, which is called a bracket. And here you can see it's a combination of actually 2 rather simple geometries. It's one block structure, and then another structure, a wall structure, is added on top of it. So the challenge when processing when doing cold spray additive manufacturing, cold spray, you need to know, is actually just a surface, a thermal spray process for surface, so for coating, but due to the possibility of the process to deposit large amounts of powder very quickly, it's also gained importance as a additive manufacturing process over the last couple of years. And but what still needs to be done is to identify suitable strategies to be able to build up within a sufficient angle to the build plate. So this is rather tough. You need a very good robot planning, path planning strategy to get rectangular edges of this process. Otherwise, you always get just a Gaussian-like shape of your parts, and need to mill afterwards very much of your depositioned material away. And yeah, as you can see, it's very fast. The build time was here only 30 minutes. And this is a copper chrome zircon built on aluminum substrate. Then furthermore, we wanted to also build Inconel or alloy 718 with cold spray. This is a rather tough task because of the high strength of Inconel 718, but we managed it to get very high densities. This was actually quite a quick success we had there, but we had the problem that large material depositions of the alloy 718 detached even during the process and cracked during the process. You can see it here. That's what it looked like all the time. If we were spraying a little bit of bigger parts, let's say exceeding a diameter of 50 to 50 millimeters, the parts just cracked away from the substrate. Substrate in this case was also copper chrome zircon. And the solution was very simple actually, but nevertheless, it took quite a time to get through it. It was just increasing the traverse speed of the robot, which was guiding the cold spray gun. So we achieved a less local energy input. And by that, we managed it to get a good bonding of the sprayed sprayed material to the substrate. And the 300 millimeters per second weren't even enough during the specimen preparation. These also cracked away. But with the 500 millimeters per second, we managed to get a good bonding. substrate, which is actually one of the key features you need for processing multi-material, of course. And yeah, that's where we are now, where we want to go. Here we have a multi-material deposition of copper, chrome, zircon, and alloy 718 with the field of application. Yeah, we want to fabricate a rocket liner. And what was the first goal for that? We wanted equal material proportions. As I've shown you before, we got 2 powder feeders, and these are volumetric powder feeders. And if I, for example, set a feeding speed of 2 RPM for both of those powder feeders, I actually, of course, want nearly the same amount of powder, or equal amounts of powder of both materials in my final part. So this you can see here was with an old parameter set. We got mostly copper, chrome, zircon, and a little bit of alloy 718 with placed within it. And if you look closely, you can see that the alloy 718 hasn't really deformed yet. So actually, this is not. It's just was embedded into the copper, chrome, zircon, but actually the alloy 718 was not really cold spread, as it didn't plastically deform actually. And with the new parameter set, with a few adjustments, especially regarding pressure, temperature, we managed to get to plastically deform both materials, so the copper, chrome, zircon, and the alloy 718. To get a rather homogeneous multi-material application of both materials onto a copper, chrome, zircon substrate. So why is this important? Because when we are building up a rocket liner, we want a sufficient or a reliable material transition from copper, chrome, zircon to alloy 718, and that's why we first want to spray copper, chrome, zircon. Then we want to spray the mixture of both materials, and afterwards pure alloy 718. And this multi-material here means especially the material transition, the continuous material transition, as I mentioned within the introduction. Yeah. Let's have a short outlook. What are the next steps? We want to examine, as I've told you, different build-up strategies to enable the fabrication of a complete liner with cold spray. So at the moment, we are able to build up rectangular edges, so block structures, wall structures, but we need to step that up to get to be able to build a complete rocket liner. And at the moment, what's going on, we are testing, we are mechanically testing the sprayed materials in the as-built stadium, as well as in a heat-treated stadium. And you can see it on the right side here. We got our one of our blocks of alloy 718 heat-treated within our vacuum oven. So thank you very much for your interest in my presentation. Feel free to ask me questions now or later. Here you got my contact data. Just feel free to write me an email. Thank you very much.
Thank you, Philipp. That was a really interesting presentation. And now we have actually run out of time, but shortly I will try to get some questions. Paul answered his questions directly. Thank you, Paul. So I will take care of some questions for Adeline. Okay. So Adeline, how many of these parts are today in regular production or flying? Asked Pollard. And also he asked, how do you see the wire competition against powder in AM?
Yeah, so about the number of parts in aerospace, unfortunately, there is no public statistics, and in a number of cases, parts are not public. The serial part, we see mostly prototypes. But what is for sure is the number is increasing every year. So it is more and more parts being qualified progressively in different materials for aerospace, both in engine and aircraft structure, but also in many other aero-related applications and space applications, such as helicopters, rocket engines, and so on. Satellites. Maybe as before tackling the other question, maybe which was on
it is how we compare powder and wire. Yeah,
so we have some points highlighted, I think, by Paul, some preliminary answer on the topic, but so we don't at EPMA so much focus on wire-based processes, nor on polymer or other materials, because focus of EPMA is powder metallurgy, so metal powders, and all the processes. What we see is there are research and development works going on both on wire and powder-based processes. To my knowledge, neither are really used massively in production compared with SLM or laser beam melting LPBF process, which is more widely adopted process for the in the field of additive manufacturing today for part manufacturing. I wanted also to add a word and say, because I forgot to mention it, that there is also the plan to add a cold spray section in the new edition of the additive manufacturing brochure. We'll have some contribution from Fraunhofer IGCV thanks to Georg Klick. And I also encourage speakers, so Paul and Philipp, if possible, to provide the case studies or images of the processes which were shown, because it's a good way to highlight everything what is going on in the technology development and applications of new processes in additive manufacturing in particular.
Okay, thank you. As I said, Paul has already answered these questions, and there are some questions for Philipp as well. So Philipp, are you using HIP after AM?
Yeah, just answered that within the chat. At the moment, we are not using it, but we will have to. We will have a look in the future on it. But at the moment, with cold spray, we achieve very high densities for our materials, and for the PBF LB, I think my colleagues are having an eye on that.
The final one. How do you progress with the direct melt AM you mentioned?
What direct melt AM? So you mean the PBF LBM?
The level of success, maybe. Yes, direct melting AM. I couldn't understand from Philipp Walls.
Philipp, do you mean the cold spray or the PBF LBM? So I think with both, so let's just answer me for both. I think with both progresses, as I've shown you, the latter. Okay, with the cold spray, yeah, we've managed to get over the first starting problems, as I would say. We got our system since 2020, and at the moment we are focusing on more like the problems of the plant technology itself. So we got a huge amount of what's the I don't know the word. The nozzle wear, sorry, we got as a central element. I've shown you the nozzle, and the nozzle it's a central element, but it's also it's a crucial element of the system, but it's also the weakest part of it, as it tends to wear very hard. And so we need to focusing on setting the parameters in a way that we have that we have a constant nozzle geometry during the whole process. So that's where the biggest actually the biggest task is at the moment. Especially for the high strength alloys, as they wear the nozzle harder than, for example, pure copper. And that's where we've made already progress, but it still need to be a lot more improved on the fabrication of the different materials. I think we made some good progress. So we managed to copper chrome, pure copper, tungsten tantalum and stuff. We managed to spray it. Even tool steel was now sprayed successfully. So on this side of the process, actually it goes quite well, I would say. I hope this answers your question. Yeah.
I hope so. Thank you very much. So I need to close the session now. We are already exceeded the timeline. Okay, I would like to thank everyone for joining the seminar, and I hope that this session has been really fruitful for you. And as I mentioned at the beginning of the webinar, please follow us from our project website and social media. Our next and final webinar will be held in June by EWF, the European Welding Federation, who is the coordinator of some project, as a final wrap-up of the project with conclusions. And we hope to see you there back again as the project team. Until then, have a great day and thank you. Thank you. Goodbye.
Thank
See
you
you.
all.
Bye-bye.
Goodbye.
Goodbye.
Goodbye.